Okay, here we go with a video about practice exam 2. And these are obviously the free response questions. This is question 1 over here. So we'll just check it out. It says you have two blocks, 4m and m. They're sliding across a horizontal surface with a constant speed VO, and then a compressed spring of negligible mass between the blocks. And then there's a string between the blocks to prevent the spring from pushing the blocks apart. As the blocks move, the string breaks and the blocks are pushed away from each other by the spring. After the spring loses contact with the blocks, block 1 is at rest, so this is V equals 0, and block 2 is moving to the right, so that one's moving to the right over there. Okay, let's look at what the questions are asking. So here is part A. It says the diagrams in figure 2 can be used to represent the momentums of block 1 and block 2 before the string is cut. So we're going to be filling in some arrows over here, and the momentum vector for block 1 before the string is cut is shown. Draw arrows to represent the vectors of block 2 before the string breaks and blocks 1 and 2 after the string breaks. It should start at the 0 line, should be proportional to the length, and a 0 would be just a dot. So before the spring breaks and then after the spring breaks is over here. So block 1 is not moving after the spring breaks, so that's pretty easy to do. So that's just going to be here. And block 2 before the string breaks, not the spring, before the string breaks, well, they've put block 1's, let me put this up. They've put block 1's momentum as 1, 2, 3, 4. So its momentum was 4. And it had a mass of 4m. So we could assume the mass is 1 and the speed is 1, and therefore its momentum is 4. If the speed is 1, block 2 has the same speed. And if m is 1, then its momentum is just going to be 1 times 1, so it'll be 1. So this should be just going over to the 1 spot right there, just like that. Okay, so now we have after the string breaks, well, momentum has to be conserved. So before we had 5 going to the right, so that means this one has to be 5 going to the right. 1, 2, 3, 4, 5 going to the right, just like that. There you go. Now to question A, part A, 2, derive an expression for the potential energy initially stored in the compressed spring. Express your answer in terms of m, VO, and physical constants. Begin your derivation by writing a fundamental physics principle. So this graph does not go with that one. So we are deriving an expression for the potential energy stored in the spring. And we're trying to figure out what physics principle or equation we can use to start out. Well, there's two that I could think of. One of them is conservation of momentum. So we're going to be adding up the initial momentum and setting it equal to the final momentum, something like that. And then the other thing is the potential energy initially stored in the spring. All of that is going to get released as work that's done on the blocks. So we could have a work is change in kinetic energy. I think that's the other one that's going to go there. Let me get myself some space and work over on this page over here. So we're going to start off with really, and oh, by the way, we're looking to express it all in terms of m and VO and physical constants as appropriate. So this is going to be a conservation of momentum problem. So remember, when we have explosions, when things move apart from each other, we have conservation of momentum. So we'll just start out by writing the initial momentum equals the final momentum. Sum of initial momentum equals sum of final momentum. And then we can just write this down. So we have beforehand, we've got 4m plus m, that's our masses, times VO. That's our initial momentum, m times v. And then this one has 0 momentum after the spring goes. So this one is just going to be m times vf. And from here, we can figure out what vf is. That's pretty easy to do. This is 5mvo equals mvf. So the masses go away. And then this is going to give us that vf is 5vo. So how is that useful for us? So the other thing we're going to be looking at is the change in kinetic energy. And how much the kinetic energy changed is going to be how much energy was stored in the spring. So the spring is changing the energy of the system. That's the only thing that's doing work on the system. So the change in kinetic energy will be a final kinetic energy minus an initial kinetic energy. And then this is going to tell us the energy that's stored in the spring, because that energy did work on the blocks over here. So this is pretty easy to do. This is 1/2 m, since it's just this block, times vf squared and then minus 1/2 times 5m times VO squared. We're allowed to have VO in our answer. We're not allowed to have VF. So we're just going to substitute that in for there. And then, so that is 1/2 m 5VO squared minus 1/2 5m VO squared. Scooch this up a little bit. I'm going to pull out 1/2 m and VO squared. And so then that's going to give me, well, that's 5 squared, 25 minus 5. 25 minus 5. And then that's 20, so half of 20 is 10. So it's 10 mVO squared. And that's your answer. That's the change in kinetic energy. And that's the work that was done by the spring. Okay, now we're going to move on back over here. And this is the next question. So it comes down on this next page. So let's move over to this page over here. So it says part B. In a later scenario, block 2 is placed at rest on a horizontal surface. A force that varies as a function of time is exerted on the block as shown in figure 3. So right away when we're looking at a force and time, we're thinking of some sort of impulse thing. We've already dealt with momentum, so it's probably going to be an area and it's probably going to be an impulse, more than likely. During the time interval there to there, the force increases linearly, and then during this time interval, it's a constant force. Another time, the force is no longer exerted, and this is the final speed of the block. So it's kind of weird, but it's just like a completely separate problem where all you've got is a block that's got a force on it. So no spring, no nothing, no collision, nothing like that. It's like a completely different scenario. Derive an expression for a time t2 in terms of m, f1, t1, and v2, and physical constants. Begin your derivation by writing a fundamental physics principle. So the fundamental physics principle we're going to write down is the integral of f dt is going to be change in momentum. So that's impulse equals change in momentum. Oops, let's scooch that up a little bit. Impulse should change in momentum. That's our fundamental thing. And then we're going to have to figure out these two things kind of separately. So let's figure out the integral of f dt part. So back up here, we're just looking for areas. We've got two different areas to deal with. This area and then this area. This one is going to be half of f1 t1. So that's 1/2 f1 t1. And then this area right here is f1 times the difference between these two. So it's going to be f1 times t2 minus t1. That's just straight up geometry right there. So it's interesting to write this integral down here. What we're really talking is about area. So you could even just write down area, and then you could write down it's going to be 1/2 f1 t1 plus f1 times t2 minus t1. Cool. And now we have to figure out the change in momentum side of things. So that is going to be the final momentum minus the initial momentum. And it's just a block over here. So the final momentum is going to be mass times the final velocity, which they called v2. So mv2. And then the initial velocity 0 because it starts from rest. Let's just double check. Placed at rest. Good. Double check that one. So it's placed at rest. And so that's our change in momentum. So these are going to equal each other. So now I said this is just mv2. So this is equal to mv2. And now we're supposed to solve for t2. So then that's just a little bit of algebra from here to solve for t2. I would say turn this into, there's nothing really so easy. So this is 1/2 f1 t1 plus f1 t2 minus f1 t1 equals mv2. So here's an f1 t1, here's an f1 t1. So this is going to be f1 t2 that, if I take, this is going to be minus 1/2 now because I got plus 1/2 and minus 1. So minus 1/2 f1 t1 equals mv2. And then just algebra wise, I don't know, t2 is 1 over f1 times f1 t1 plus mv2. I don't know, not very pretty, but there it is. That's how it is. Cool. So that is the practice question number 1. I think I'll split these videos up into parts, so we'll move on to practice question 2 in the next video.